assure ourselves, as I said, that every pair of options across all the possible pairs of factors identified in the table have been tested at least once. All right, so what is the logic behind this? Why would we think that this would be, quote unquote, enough? Well, we know from the theory of equivalence partitioning that there are things that should be treated equivalently, and we want to make sure that we test those, and that's broad testing as covering of equivalence partitions, or a little bit more extensively the boundary values that exist. And the theory there is, that all these things are supposed to be handled the same way, right? So there's going to be a problem with any one of them. There's going to be a problem with all of them. And so by selecting a representative out of the equivalence class, or maybe two representatives at the edges, that if there's a problem with a particular option, then that's likely to come up. Now, what we're going to do here is we're going to build on that concept by saying, okay, yeah, there are definitely lots of problems that arise that way. There are also some problems that happen when two particular options are combined with each other. So they're fine by themselves, and thus equivalence partitioning and boundary value analysis would not get at the problem. But when you get them together, that specific combination of options together, then they misbehave in some way. They don't do what they should do, or they do what they shouldn't do, or they disable something else that's supposed to happen from happening. And, this is concept of unwanted option interaction that occurs. Now, that's the hypothesis, that it's important to test the singletons, the representatives of the equivalence class, possibly by extension the boundary values of that class. And we're also going to try to test the pairs of the equivalence classes. But we're not going to worry about triples, and we're not going to worry about quadruples and quintuples and so on and so forth. We're not going to worry about higher order combinatorial tests because of the law of diminishing returns, basically, that the cost of covering those is disproportionately high. Empirically, the number of observed failures that are triple specific or quadruple specific, in other words, that rely on a very exquisitely precise combination of options, are fairly rare. And therefore we would spend a lot of money chasing after bugs in situations where we would be unlikely to find them. Now, I'm not going to get into the empirical data behind this. If you would like, there's plenty of documentation on orthogonal arrays and their use and why testing pairs is good enough out there on the internet that you can do further research on this. I'm going to basically take it as axiomatic at this point, take it as a given that this is the case, that going beyond pairs of options is going to be beyond the cost-benefit analysis, if you will, for testing, and therefore that this is something that's justified. Again, there is plenty of internet-based empirical material out there that you can look at, and if you're still kind of going, well, I don't know if I buy that, you try to convince yourself. And then, if in the alternative, if you cannot convince yourself, just run it through the practicality gauntlet and say, okay, well, suppose that bugs are just as likely to happen in triples as they are in pairs. Well, what's it going to cost me to cover all the triples? What's it going to cost me to cover all the quadruples? So I think both from a likelihood of finding problems and a cost to find problems approach, or a technique or analysis, it stands to reason that pairwise approaches make a lot of sense. Okay, so those of you who don't believe that at all, feel free to hang up now, because the rest of this is about how to actually implement pairwise testing on the assumption that you believe and accept that it is sufficient. And a gentleman in the session this afternoon who seemed very disturbed by this, and I think he needed to attend a different discussion about why it was sufficient. I see that nobody's dropped off, so you're all either convinced or willing to suspend your disbelief for the moment. Good. So there are two techniques that we can use to do pairwise testing. I'm going to explain one of them. I only need to explain the one because the other is self-explanatory, or at least the explanation is bundled with the tool. So one approach is what's referred to as an orthogonal array. And there's a big library of orthogonal arrays out here at this website. You'll notice that there's a really interesting and important phrase here, set of characters, ATT. So this is an AT&T website, and they are obviously very interested in combinations of settings because phone switches and other such phone network equipment has a lot of different settings in it. So they have a big library of orthogonal arrays that they put out there in, I'd say the public domain. They're willing to share it with you at no charge. You just go out and download it. Now the question is how to download, which one to pick, and that is a question that we will answer shortly. Now another option, if you don't feel like going through the process that I'm about to explain to you, which is fairly simple, but does require a little bit of Googling around and screwing around looking for the right orthogonal array, is to go to this website here, pairwise.org, and there are a bunch of freeware and commercial all pairs tools out there, multiple freeware tools available. In fact, the National Institute of Science and Technology, I believe, in the United States, put out a very robust pairwise testing tool that in fact is almost the equivalent of a classification tree tool, which I might talk about a little bit later in another one of these webinars. It's a very sophisticated tool and it's available for free. I don't know if you're going to be able to find it at that website. You might. Try a web search for NIST pairwise software testing and see if that comes up with it. If anybody can find it, send me the link during this webinar. I'll be happy to push it out to all the attendees. Excuse me for just a second. No, thought I had a sneeze. Didn't have it. Okay, now, you can use either one of these approaches, orthogonal arrays or all pairs tables. Now, there are some subtle differences. I have never been in a situation where the difference mattered. I've had some people who told me that they thought the difference mattered, but those people were also involved in trying to sell a pairwise testing tool that generated orthogonal arrays, so I'm not sure I would consider those people unbiased sources. Anyway, there's the subtle difference is that the number of times that each pair of options is represented is equal in an orthogonal array and not necessarily equal in an all pairs table. The likelihood of that mattering, if you're using this for compatibility testing or for functional testing, as far as I can tell, is 0. So I wouldn't worry about it. Use whichever one you prefer. If you prefer to use a tool to completely automate it, do that. If you're comfortable with the orthogonal array technique I'm about to show you, then do that. Okay. Well, I've been dying of suspense. What's an orthogonal array? And here it is, an orthogonal array. Okay, now, an orthogonal array is a mathematical construct that has the property that every pair of options across every possible pair of factors